Hello, I'm ADITI SHEEMAR from Bennett University, and today I'm going to explain Sparse and its various aspects in machine learning. What is sparse? In AI inference and machine learning, sparsity refers to a matrix of numbers that includes many zeros or values that will not significantly impact a calculation. Sparse is the representation of items by the strong activation of a relatively small set of neurons. This is called sparse data because most of the sensor outputs are zero, which means those sensors are functioning properly, but the actual reading is zero. Although this matrix has high dimension data, it can be said that it contains less information. What is sparse data? You might have started hearing a lot about sparse data in big data and its advancement in near future along with its impact on the infrastructure of networking. If well managed and planned, sparse data can turn out to make an entire company or organization much more efficient. But if left to growth and population on its own, it could easily overwhelm the servers by flooding it with information, resulting in a kind of death by thousand small cuts. Typically, sparse data means that there are many gaps present in the data being recorded. For example, suppose a sensor data in the sensor may be sending a signal only when the state changes, like when a movement of door in a room. This data will be obtained intermittently because door is not always moving. Hence, this is sparse data. However, if the sensor records, say, wind speed, the value changes constantly. Thus, the dataset that is obtained in dense is dense. Sparse data is also known as such because the information that is represent it's rare. This then turns to make the information very valuable for the business owners. Organization often make assumptions about their clients based on sparse data that has been collected by them. Here are some of the benefits of sparsity in machine learning. Consideration of sparsity in machine learning can have three benefits. Firstly, reduce space. When dataset is known to be sparse, amount of required memory and can be reduced sustainably using a sparse representation. Secondly, reduced runtime. When many numbers have same default value, corresponding calculations can be done only once to reduce runtime. Thirdly, reduce generalization error. Sometimes sparsity is a favorable property for a portion of an ML model. This may be due to a principle such as Occam razor or known as facts about the problem in hand in such a case. Considering the sparsity in model will reduce generalization error leading into more powerful model. Now let's come down to the fact that how will you identify if your data is sparse or not? The amount of data in a dataset relative to the amount of users is known as the density of dataset. By collecting the data and inserting it into a matrix, one can identify how dense or sparse a dataset is. The more information there is relative to the amount of users, the denser is the data. The density of the data used has a huge impact on the final prediction of accuracy. A higher density generally results in more accurate predictions since there is more data to learn and train from. With a larger amount of missing values, the data set is considered sparse, making accurate predictions more difficult to acquire. Data sparsity is widely considered as a key cause for unsatisfactory classification accuracy. Sparsity can, for example, occur when a user forgets to enter certain explicit data when signing up to a website, leaving the data sets with sparsity levels above 90%. Some classification algorithms perform better than others when dealing with sparse datasets. Naive Bayes classifiers are considered high performance when dealing with sparse data. When encountering a missing value, the algorithm omits the property in its calculations, which is the only applicable due to the assumption on all attributes are independent. A variable with sparse data is one in which relatively high percentage of variable cells do not contain actual data. Such empty values take up storage space in a file. Now, here are some of the problems with sparse data and the ways with which we can handle them. In today's society, software and apps based on machine learning and predictive analysis are the essence. Machine learning has provided us with possibility of predicting likely future outcomes based on previously collected data in order to save time and resources. A common problem in machine learning is sparse data, which alters the performance of machine learning and algorithms and their ability to calculate accurate predictions. Data is considered sparse when certain expected value in a dataset are missing, which is a common phenomena in general large scale data analysis. A general problem regarding public data sets is sparse data, which is a recognized challenge when working with machine learning with classifiers. Sparse data refers to data that is incomplete and can have an immense effect on the ability to train the classifier into producing accurate predictions. Firstly, here are some of the ways through which we can handle these problems. Firstly, handling missing values. Most classification algorithms have been developed for handling data without any missing attribute and therefore require completely dense datasets in order to compute predictions. Since sparse datasets are very commonly and most algorithms cannot handle missing values naively, techniques for solving missing data issues are widely used. The most common techniques to approaches for you eliminating the data sparsity when using algorithms without an internal way of handling the missing values. Not all techniques are presented in this report, and alterations to techniques are common. On the other hand, certain algorithms actually have an AI way of handling sparsity and do not require any type of pre processing of data in order to work. Secondly, mean median mode imputation. Mean imputation is the process of calculating the mean value of all the values and attributes, allowing it to replace the missing value. If attribute is not numerical, mode imputation is used, which is letting the most frequent value of attribute replace the missing value. Estimating missing value through imputation is considered viable when handling small amounts of sparse data. By using imputation on data of low sparsity, the likelihood of large deviation is results in less likely. Mean or mode imputation is the most commonly used method for handling sparse data. Lightwise deletion. The lightwise deletion methods involves removing or ignoring entire observations from the dataset if observation in question contains a missing attribute value. The obvious drawback of this method is, however, that potentially viable and important data may be excluded in the calculations and may severely bias the results. Next is internal sparsity handling. As Fawn mentioned, most machine learning algorithms require a completely dense data set without missing values in order to work. There are, however, exceptions, such as the case of naive Bayes algorithm, some decision tree algorithms. Such classification algorithms are able to handle missing values natively, and meaning that they can compute predictions on sparse data without using any type of prior pre-processing. The 10 algorithmic calculations include missing values, making the sparsity a part of final prediction. Lastly comes the J48. The J48 algorithm uses the C4.5 strategy for handling sparsity, which is commonly the decision tree algorithm. When the classifier encounters a missing value and therefore cannot go further down the decision tree, the probability distribution of the possible decisions is calculated to find the most frequent outcome. The J48 classifier follows the branch in decision tree order in order to produce its prediction for the observation containing the missing value. Now let's understand sparse features. Features with sparse data are features that have mostly zero values. This is different from features with missing data. Example of sparse features include vectors of one hot encoded words or counts of categorical data. On the other hand, features with dense data have predominantly non-zero values. Here are some of the difficulties in machine learning due to sparse features. If the model has many sparse features, it will increase the space and time complexity of models. I mean, linear regression models will fit more coefficients, and tree bias models will have greater depth to account for all features. Model algorithms and diagnostic measures might behave in unknown ways if the features have sparse data. This shows the goodness of fit tests are flawed when data is sparse. If there are too many features, models fit in the noise in training data. This is called overfitting. When model overfit, they are unable to generalize to newer data when they are put into production, and this negatively impacts the power of models. It impacts the predictive power of the models. Some models may underestimate the process importance of sparse features and give preference to denser features, even though sparse features may have predictive power. Tree-based models are non-notorious for behaving like this. For example, random forest overpredicts the importance of features that have more categories than those features that have fewer categories. Here are some of the methods for dealing with them. Firstly is removing features from the model. Sparse features can introduce noise, which the model picks up and increases the memory needs of the model. To remedy this, they can be dropped off from the model. For example, rare words are removed from text mining models, or features with low variance are removed. However, sparse features that have important signals should not be removed in the process. LASSO regularization can be used for decrease the number of features. Rule-based methods like setting a variance threshold for including features in the model might also be useful. Secondly, make the features dense. Principal component analysis (PCA) methods can be used to project the features into directions of the principal components and select the most important components. Feature hashing. In feature hashing, sparse features can be binned into the desired number of output features using a hash function. Care must be taken, of course, to choose a generous number of output features to prevent hash collisions. Thirdly, using models that are too robust to spare features. Some version of machine learning models are robust towards sparse data, and may be used instead of changing the dimensionality of the data. For example, the entropy weighted K means algorithm is better suited for this problem than the regular K means algorithm. So, sparse features are common in machine learning models, especially in the form of one-hot encoding. These features can result in issues in machine learning models like overfitting, inaccurate um, feature importance, and high relevance. So it is recommended that sparse features should be pre-processed with methods like feature hashing or removing the feature to reduce the negative impacts on the results. Now let's come down to sparse matrices. Sparse matrix is a matrix in which most of the elements are zero. On the contrary, a table in which majority of elements are non-zero is called dense. We define the sparsity of a matrix as the number of zero elements divided by the total number of elements. A matrix with sparsity greater than zero point 0.5 is a sparse matrix. When working with sparse matrices, it is recommended to use dedicated data structures for efficient storage and processing. Pandas provides data structures for efficient storage of sparse data. In these structures, zero values are not actually stored in the array. We can use these structures to reduce the memory usage of our data. You can think of this as way to compress a data frame. It is possible to create a sparse data from directly a frame directly using the sparse parameter in pandas using get dummies. This parameter defaults to false. If true, the encoded columns are returned as sparse array. By setting sparse equal to true, we create a sparse data frame directly without previously having a dense data frame in memory. Example is given below in the picture. Using sparse data option in one hot encoding makes our workflow more efficient in terms of memory and usage as speed. A matrix is sparse if uh, of its components are zero. The interested in areas because its exploration can lead to enormous computation savings and many because large matrix problems that occur in practice are sparse. In scientific computing and numerical analysis, a sparse array or sparse matrix is a matrix where a large portion of components are zero. There is no precise meaning of the number of components that should be zero for matrix to be viewed as sparse, yet a typical measure that is the number of non-zero components is generally the number of columns or rows. A sparse array is an array of data where numerous components have an estimation of zero value. This is as opposed to dense array where the vast majority of the components have non-zero values or full number of numbers, full of numbers. This is the formula for sparsity. Now let's come down to some of the problems due to it. Firstly, time complexity. Assuming an enormous sparse matrix can be found a way into memory, we will need to perform the produce procedure on the matrix. Basically, if the matrix generally contains zero values, for example, no information at that point performing tasks across the matrix may take quite a while, where the majority of the calculation performed will include adding or increasing zero values together, right? And secondly, space complexity. Very huge sparse matrices require a ton of memory, and some huge matrices that we wish to work with are sparse. An illustration of an extremely huge matrix that is too enormous to even consider being but put away in memory is a link matrix that shows the links staring with one side onto the next. Sparse matrix comes up in encoding plans utilized in planning of data. Sparse matrices come up in some particular sorts of data, most quietly quiet perceptions that record that event or check a movement of sky. Skyfi gives apparatuses for making sparse matrices utilizing various data structures, just as devices for changing a dense matrix over to a sparse matrix. It is an open source and free Python library utilized for technical computing and scientific computing. Both SciPy and NumPy are modules of Python, and they're utilized for different activities of the data. Then again, Sky contains all the mathematical functions, some of which are there in NumPy, somewhat and not in underiable structures. A dense matrix put away in NumPy array can be changed over into a sparse matrix utilizing the CSR matrix portrayal by calling the CSR matrix function. Here are the types of sparse matrices. Firstly, the row-based list of list sparse matrix. Second, the dictionary of keys-based sparse matrix. Third, the sparse matrix with diagonal storage. Fourth, compressed sparse row matrix. Fifth, compressed sparse column matrix. Sixth, sparse matrix in coordinate format. And lastly, the block sparse row matrix. So, large sparse matrices are common in general and especially in applied machine learning, such as in data that contains counts, data encodings that map categories to counts, and even in whole subjects of machine learning, such as natural language processing. It is computationally expensive to represent and work with sparse matrices as though they are dense and much more improvement in performance can be achieved by using representation and operations that are specifically handle the matrix sparsity. The solution to representing the work and the working with sparse matrices is to use an alternate data structure to represent the sparse data. The zero values can be ignored and only the data or non-zero values in sparse matrix need to be stored or acted upon. In order, the order in which a sparse matrix is filled can be an enormous can make an enormous difference in computation time. To fill a sparse matrix quickly, the elements should be addressed in a sequence that corresponds to storage order of the sparse matrix. By default, the storage order in a agent's sparse matrix is column major, but it is easy to change this. When working with large sparse data sets, it is highly recommended to convert our Panda data frame into a sparse matrix before passing it to sklearn. The solution to representation and working with sparse matrices is to use an alternate data structure to represent the sparse data. The zero value can be ignored and only the data with non-zero values can in the sparse nature should be need to stored or acted upon. There are multiple data structures that can be used to efficiently construct a sparse matrix. Three common examples are listed below. Firstly, the dictionary of keys, that is, a dictionary is used where a row and column index is mapped to a value. Secondly, lists of list, where each row of matrix is stored as a list with each sublist containing the column index and value. Thirdly, coordinate list. A list of tuples is stored with each tuple containing the row index, column index, and the value. There are also data structures that are more suitable for performing efficient operations. Two commonly used examples are listed below. Firstly, the compressed sparse row. The sparse matrix is represented using three one-dimensional array for the non-zero values and the extents of rows and the column indexes. Secondly, the compressed sparse column, the same as compressed sparse row method, except the column indices are compressed and read first before the row indices. Thirdly, the compressed sparse row, also known as CSR for short, is often used for to represent, sparse data matrices in machine learning given the efficient access and matrix multiplication that it supports. So the solution to representing predicting and working with sparse matrices is to use an alternate data structure to represent the sparse data. The zero values can be ignored and only the data or non-zero values in sparse matrix need to be stored or acted upon. Now let's come down to the interesting sparse data structures in Python. SciPy provides tools for creating sparse matrices using multiple data structures, as well as tools for converting a dense matrix to sparse matrix. Many linear algebra, NumPy, and SciPy functions that operate on NumPy arrays can transparently operate on SciPy sparse arrays. Further, machine learning libraries that use NumPy data structures can also operate transparently on SciPy sparse arrays, such as Scikit Learn for general machine learning and Keras for deep learning. A dense matrix stored in a NumPy array can be converted into a sparse matrix using CSR representation by calling the CSR underscore matrix bracket function as visible on your screen. And below is the example where we have defined a 3 sparse matrix as a dense array convert into a CSR sparse representation and then convert it back to a dense array by calling the toDense function. Here is an example of running the first prints, the defined dense arrays followed by the CSR representation and the reconstructed dense matrix. NumPy does not provide a function to calculate the sparsity of a matrix. Nevertheless, we can calculate it easily by finding the density of matrix and subtracting it from 1. The number of non-zero elements in a NumPy array can be given by the count underscore non-zero function, and the total number of elements in array can be given by size property of array. Array sparsity can therefore be calculated as below the formula which is given. You can take a look at it. Here is an example demonstrating how to calculate the sparsity of an array, and right below there is also an example of that how define sparse matrix and followed by the sparsity of matrix. Sparse matrix types in SciPy. There are many ways to represent sparse matrix. SciPy provides 7 of them, as shown below: the block sparse row matrix, coordinateless matrix, compressed sparse column matrix, compressed sparse row matrix, sparse matrix with diagonal storage, dictionary of keys based on sparse matrix, row based linked with sparse matrix, and each format has its pros and cons, so it is important to know about the difference between them. Coming down to linear regression. In statistics, linear regression is a linear approach for modeling the relationship between a scalar response and one or more explanatory variables, also known as dependent and independent variables. The case of an explanatory variable is called simple linear regression for more than one. The process is called multiple linear regression. The term is distinct from multivariable linear regression, where multiple correlated dependent variables are predicted rather than a single scalar variable. In linear regression, the relationships are modeled using linear predictor functions whose unknown model parameters are estimated for data. Such models are called linear models. Most commonly, the conditional mean of response given the values of explanatory variables or predictors, you can say, you know. is assumed to be an affine function of values. Less commonly, the condition, median, or some other quantity is used. Like all forms of regression analysis, linear regression focuses on conditional probability distribution of response given the value of predictors rather than on joint probability distribution of all these variables, which is domain of multivariance analysis. Input values x and output values are numeric. Here is linear regression model representation. Linear regression is an attractive model because the representation is so simple. The representation is a linear equation that combines a specific set of input, the solution, to which the predicted output for that set of input values. As such, both the values and the output value are numeric. The linear equation assigns one scale factor to each input value or column called a coefficient and represented by the capital Greek letter beta. One additional coefficient is also added, giving the line an additional degree of freedom. You know, example moving up and down on a two-dimensional plot, and is often called intercept or the bias coefficient. Coming down to sparse machine learning. Sparse machine learning refers to a collection of methods to learning that seek a trade-off between some goodness of fit, measure sparsity of the result, the latter property allowing better interpretability. In a sparse learning, classification task, for example, the prediction accuracy or some other classification measure of performance is not the sole concern. We also wish to be able to explain what classifier means to a non-expert. Thus, if classification task involves, say, gene data, one wishes to provide not only a high-performance classifier, but also that only involves a few genes, allowing the biologist to focus their research efforts on those specific genes. The lasso. Fitting a sparse model that uses a subset of available predictors is equivalent to learning a weight vector beta that only contains a small number of non-zeros. As we saw in the case of sparse signal representation and underdetermined inverse problems, penalizing the one norm is an efficient way for promoting sparsity. In statistics, one norm regularized least square is known as the lasso. Here is the formula given below, which you can take a look at. Lambda greater than 0 is a regularization parameter that controls the trade-off between the fit to the data and one norm of weights. With 50 predictors where the response only depends on 3 of them. If lambda is very large, all coefficients are equal to 0, and if lambda is very small, the lasso estimated is equal to least square estimate. For values in between, the lasso yields a sparse model containing coefficients corresponding to relevant predictors. So here the lecture ends. Thank you so much for watching, and I would also like to thank my mentor, Mr. Umesh Gupta. Thank you so much.